Let's continue thinking about strain and we'll look at some examples. All right, here's one example. You have a 100-inch long column, you put a load on it, and it gets 1/10 of an inch shorter. What is the strain? I have put our strain equation into one of these triangles, a Müller diagram. So strain equals deformation over length. We're trying to find the strain. All right, so strain is deformation over length. Do we know the deformation? Yep, it's 0.1. Do we know the length? Yep, it's 100. Good. So we can figure out strain equals 0.1 divided by 100 equals 0.001, or 1,000th. And again, no units. Let's think about stretching something. This is an example of a tensile tester, or a tension test machine. It's used for measuring the actual strength of a piece of material, often a piece of steel. And so you clamp the bar in here and you measure. You start out with 2 dots, usually 2 inches apart, and you measure how far apart are they when you apply a certain amount of force. So that's what happened in this problem. Here's a tensile test specimen. The marks were originally 2 inches apart. It was tested, and the marks became 2/1000ths of an inch farther apart. What is the strain? We're looking for strain. We know deformation is 2/1000ths. We know the length was 2 inches. So to find strain, we can say 2/1000ths divided by 2 will give us 0.001, or 1,000th. Now let's switch it up a little bit. We have a weight hanging from this rod. The rod is 100 inches long, and the rod registers a strain of 0.001 when you attach a weight to it. How much does the rod elongate? Well, how in the world do you know how much strain there is? The answer is you use a strain gauge. Here is a physical, mechanical example of a strain gauge. These are pretty inexpensive. They have a path of conductor, like copper, printed on a piece of foil, and you attach it to your structural member with adhesive, and then you apply the load. If the thing gets stretched out longer, the electrical resistance increases, and if the thing shortens, the electrical resistance decreases, and you can measure that on a meter and determine how much the strain was. You can also get, it's very common to get electronic devices now, transducers, that will measure the strain. So that's how we determined the strain on this 100-inch bar. How much does it elongate? Well, we're looking for deformation, so let's cover up the deformation in our triangle. And we are left with strain times length. Deformation is strain times length. Strain was 0.001. Original length was 100 inches. So the deformation is 0.1 of an inch, or 1/10 of an inch. Notice that this does have units. This is in inches because we had strain with no inches times length that did have inches, so we come out with inches. And deformation is a length, so of course it would be in inches. All right, we have a column that's 40 inches high. We put a load on it, and we get a strain of 0.002. How much does the column shorten? So we're looking for deformation. We've got strain, 0.002. We've got length, 40 inches. So we're looking for deformation equals strain times length. Let's do that. Deformation equals strain, 002, times length, 40 inches. It shortens 0.080 of an inch, 80 thousandths of an inch. And again, the units are in inches. Okay, so let's look at the problems in our quiz coming up. First one, I bet you can answer this one easily. In what units is strain measured? Second question has to do with one of those tensile testers. We put a steel specimen inside our tensile tester. It starts out with gauge marks that are 2 inches apart. It elongates 2.4 thousandths of an inch. It elongates 0.0024 of an inch between marks that were originally 2 inches. What is the strain? So we're trying to find strain. Do we have deformation? Yes, we do. 0.0024. Do we have length? Yes, we do. 2. Could we find the strain? Yes, we could. There's our equation. Next problem. We've got a reinforced concrete column. Like you might find here, this is the LCC main campus. Actually, this driveway was before we did some renovation. I kept this picture because I think it does a good job of showing these columns, and I like them. Anyhow, so we've got a concrete column that's 12 feet long. We put a load on top of the column, and it shortens 1/8 of an inch. Determine the strain. Oh, well, we're trying to find the strain. Do we know the deformation? Yes, we do. 1/8 of an inch. Do we know the length? Yes, we do. So could we find the strain? Yes, we could. However, there's one thing to keep in mind here. Notice that the deformation is written in inches, 1/8 of an inch. The original length was written in feet. So you're going to have to get both of those numbers into the same kind of units. Well, let's think about this. If the column is 12 feet long, how many inches is it? How many inches are there in a foot? 12 inches per foot times 12 feet. Aha! You can probably figure out the inches. All right, next question. We have a concrete test cylinder. And by the way, these are cylinders that you pour on a job site. When you do a concrete pour, you get test cylinders from the same batch of concrete. You let them cure 28 days, just like you do the rest of the concrete, and then you take them to a lab, and the lab applies compression and sees how much load it takes to cause this thing to crack, determining the strength of the concrete. Is it as strong as it was supposed to be? So here's a concrete test cylinder. It's 8 inches tall, 4 inches in diameter, and a load gets applied to it that results in a strain of 0.003. Question is, how much does it shorten as a result of this load? What are we trying to find? We're trying to find deformation, change in length. Do we have strain? Yes, we do. Do we have original length? Yes, we do. Do we care what diameter it is? No, we don't. That doesn't matter a bit. So we're trying to find deformation. That means if you're using your triangle method, you would cover up deformation with your finger, and you are left with strain times length. Or, if you like doing math, you could just multiply both sides by L, and you're left with strain times L equals deformation. So there's the form of the equation that we'll use to find how much does it shorten. Finally, last question. A 500-foot long steel cable is loaded in tension. Well, that might be a great big tower crane at a dock with a big old heavy load hanging from it. So the cable is 500 feet long. It's loaded in tension, got a tension force. It registers a strain of 0.005. How much does the cable elongate as a result of this load? All right, so what are we trying to find? We're trying to find deformation. How much does it elongate? Do we know the strain? Yes, we do, 0.005. Do we know the length? Yes, we do, 500 feet. So our equation would be, once again, covering up the deformation, we are left with strain times length. There's the form of our equation. Now you might be thinking, oh, wait a minute, this is in feet. No problem. Strain does not have units, it's just a number, and our original length is feet. So when you're looking for the deformation could be in feet too. And this big old thing is so long that it's probably going to be more than a foot, maybe several feet, that it will elongate. So no problem, just go ahead and leave the length in feet.